Hello guys, and welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easy to understand. Today we're talking about statics. We want things to keep still, nothing to fall, nothing to go anywhere. Okay, this is the same style of problem. We've done a bunch here on the channel already, but this is one that's a bit more realistic. We have this vehicle here holding a weight that's about 120 kilograms, causing a force downwards, and we have this fella here helping to pull it, stir it to the right, and we also have the tension here on the cable, stopping it from going anywhere. Problem statement reads, knowing that alpha is 20 degrees, determine the tension in the cable AC and in the rope BC. Okay, so this is, again, straightforward. The problem is a bit more realistic than the other ones we've tackled, but in terms of understanding, it's the same thing as before. So we have, obviously, a downward force acting upon this fella here. It's actually a 1200 Newton downward force as shown in the figure. And if we only had, if we dismiss this fella completely, pretend he's not there, if we only have this downward force here, we would have an upwards force here, upwards tension force from the cable, and that would be that. However, this fella here is actually trying to stir or to pull the weight towards his direction, so to the right of our drawing here, right, this way here, but he's too short, so not only he pulls down, but also pulls, not only right, but also down a bit, right, with the resulting force obviously being this tilted force here, right? So what that means is that he is obviously, for everything to be still, we obviously need a counter force on this direction, but also, because he's also putting some additional force downwards, we need additional force upwards on this tension here. So you can think about, a force to counter the pulling of the fella B there, plus a force to counter the 1200 newtons, right? That's the gist of this problem. But in spite of that, everything else is exactly the same. We're going to solve it exactly like we've solved all the other problems, right? What is the largest force in this system? What do I expect the largest force to be? Well, if this guy is pulling, if this guy is downwards and rightwards, and this guy here is upwards and leftwards, note that this fella is trying to negate or to reach equilibrium or to zero out the forces for the combination of these two guys, right? So I expect this AC or CA to be the largest force we have in our system. Okay, let's see if that is true or not. And what we're going to do is, what we always do is, we're going to get this force triangle here, and I lost an arrow there, but we can redo that. Here we go. Okay, and what I want to do now is recreate or create for the first time, I suppose, the triangle. So this is 5 here, 5 Celsius 5 degrees, and this is 20 degrees. Okay, so what I'm going to do, let me think about what I want to do here. I think I want to do this one here going down, and then this one here going like so. Note that if this fella here were straight up, this would never be a triangle, right? But it's not straight up. It's actually tilted 5 degrees. So this is going to be slightly tilted, and I'm not going to do it exactly 5 for us. It's going to be a very big triangle here for my drawing, but it's going to be something like this, right? Kind of thing. That's kind of the triangle we're looking at. So I'm going to exaggerate a little bit, and it's going to be this, and this is down 100% vertically down, and then like this. Okay, obviously exaggerating a lot here, but for the sake of being able to draw it all in one spot. 20. Okay, and hopefully you'll see, and let me just label things before we start losing track of what's what. This is my AC, this is my CB, and this is my 1200 newtons. So this is 1200 newtons here. This is my CB here. This is my AC here. Okay, cool. So you know that the solving of this triangle is actually super easy compared to some other triangles we've done before, right? There's really no tricks. Here we have a 90-degree angle because we have a vertical one and a horizontal one. And therefore call it green. The green angle there will simply be the 90 minus the 20 minus the 5, which gives me 65 degrees, right? So that's very straightforward. 65 degrees is one of the angles of this triangle. What about the other one? Well, the other one's super easy because you already have it, right? 65. The other one's super easy because we already have it, and it's this one here, right? What is this one? It has to be 5, right? And we've talked about that before. There's a different problem in which we do exactly that, but the idea here is if you have a line with an angle x here, and you know that this here is 180. You know that this here is 180, these two lines, right? So therefore, this blue guy here will be 180 minus x. Okay, so therefore, if I want to know this angle, y, I can do the same thing, because check it out. This is also 180. And therefore, the blue one, if I know that's 180 minus x, then I know that blue, which is 180 minus x plus the y will be 180. Okay, so 180 on both sides, which means that x equals y, right? So therefore, if this guy here is 5, then this guy here is also 5. It's the same situation we have. We do this, right? We kind of have 5 here and then 5 here kind of situation, okay? It's the same vertical line, right? So it's the same. This vertical line here is the same as this vertical line here, so therefore the angle has to be the same. And finally, obviously, this pink line here will just be the sum of the triangles, internal angles of the triangle, so that's 180 minus the 5 that we already have, minus the 65 we already have. And that is minus 70, so this is 110 degrees. 110 degrees. So that completes a triangle. We go ahead and put it more cleanly here in the corner. We don't need this anymore. We don't need this anymore. Boom. Okay, so now we have a forced triangle, and law of sines saves the day, right? The law of sines is going to say that the sine of the 5 divided by the magnitude across the 5, which is CB, will be equal to the sine of the, pick your choice, 65, divided by the magnitude of the opposite of the 65, which is the 1200 newtons. It has to be equal to the sine of 110 degrees divided by the magnitude of the AC force there. Okay, so 2 equations, 2 unknowns, straightforward. My CB will be equal to the sine of 5 degrees divided by the sine of 65 degrees times 1200 newtons, which gives me 115.4 newtons. And then, let's do it in color, AC. This will be sine of 110 divided by sine of 65. So sine of 110 degrees divided by sine of 65 degrees times the 1200 newtons, which is 1244.2. 1244.2 newtons. Okay, so this is one of the things we were looking for. This is the other thing we were looking for. And then just before we sign off, let's check to see if this makes sense. So 115 and 1244. 115, so this is right here, 1244. and this right here is 115. Okay, so as we've noted in the beginning, this guy here, this fellow here, is having to counter not only the 1200, but also the y component of the fellow pushing down on it, right? So this is interesting because often people do this kind of thing that this fellow is doing, trying to help out this person here, if it's a person or whatever, machine, whatever. And really, you're not really doing much unless you're pulling completely horizontally or horizontally plus up. You're really not helping this point. You're just making it harder. Okay, because now this guy here obviously needs to counter both the weight plus whatever force you're applying downwards. Okay, that's it for this video. I think this is good because it's quote unquote real life example. But the way of solving is exactly the same way we solve, the more theoretical ones, obviously. Beauty of engineering. If this video was helpful, consider giving it a like. If you have any questions, as per usual, just leave them down below in the comment section, and we'll talk soon.